Hi everyone, thanks for coming. My name is Brent.
And I'm Megan.
And this is our project. It might seem like a lot right now, but hopefully we can break it down in the next slides to come. We're going to start you off with a little bit of background for our project. Another chronic disease, obesity. As you might know, obesity is on the rise in the United States. According to the CDC, approximately 1/3 of all U.S. adults have obesity, and that number is rising. Now there's multiple reasons why that's the case, a combination of diet and lifestyle. We're going to focus more on diet. In the literature, fructose, a sugar, has been implicated as a contributing factor to these rising rates of obesity. And you might recognize the presence of fructose in high fructose corn syrup, which is common in a lot of the foods that we eat. One of those foods, or drinks in this case, is sugary sweetened beverages, such as Coca-Cola. To give you an example, a 12-ounce can of Coca-Cola has about 39 grams of sugar in it. That's about 4 teaspoons of sugar, half of which comes from fructose in the form of high fructose corn syrup. And to give you more background, fructose relates to the protein that we're studying. We're studying a protein called fibroblast growth factor 21. We'll call it FGF21 from now on. It has a role in the way that our bodies break down sugar, both glucose and fructose. But it's unknown whether this effect is protective or detrimental. So, for example, in mice, a high level of FGF21 indicates a resistance to weight gain given a certain diet. On the other hand, however, a high FGF21 level is indicative of the onset of obesity or other metabolic complications. And we don't really know why that difference is there, but we're focusing our study more on humans. So to give you a little bit of background about the interplay between fructose and FGF21, what you're looking at here is the FGF21 dose response. So this is the response that happens after someone consumes a beverage containing 75 grams of fructose mixed with water. We use 75 grams of fructose because we found that's an optimal dose of sugar to elicit this response. And what you're seeing here is that levels of the protein they start at baseline and then they'll increase to about 2 hours where they peak, and then they'll start to taper down after that. What you're also seeing is that this is just one subject that took the dose 3 different times. So you might notice that there's quite a bit of variability within this one subject. The peak varies at 3 different doses, even the baseline varies a little bit. And so that kind of led us to formulate our research question: why does this variability exist between subjects and within subjects?
Yeah, so here's our actual research question. So here we're asking, because we see all that variability, what we're hypothesizing is that variability may be caused by fructose in your diet. So how much fructose you eat on a day-to-day basis. And to test that, we're going to ask how prolonged exposure to fructose over a 2-week period influences levels of FGF21. And so here are our methods. So we start off with recruitment. Most of our recruitment is done through either Craigslist or BU Quickie Jobs. And then we talk to them over the phone just to get basic eligibility criteria, things like age, BMI. And then they come in for what's called a screening visit. So at the screening visit, we draw their blood. We test to make sure they don't have any underlying metabolic diseases, things like high cholesterol, high blood pressure, things like that you wouldn't necessarily know over the phone. And then they come in for 2 more visits. Those 2 are the exact same. And at those 2 visits, we do a procedure called an oral fructose tolerance test. So that's kind of what Brent was just talking about with those curves that we just saw. So an OFTT, oral fructose tolerance test, is where we give 75 grams of fructose dissolved in water, and they drink it, and we draw their blood before and 2 hours after. And the 2-hour time point is because that's where we see the FGF21 peak. So we do that at visit 2, which is like right before they start the intervention, and then 2 weeks later at visit 3. In between, this red circle is our fructose intervention. So we do a 2-week fructose challenge where people are given 14 packets of these. So I'm going to pass this around. You guys can see how much it is. It's a bit. It's about 8 teaspoons. And they have to do 1 packet every single day for the 2-week period. And they can mix it in their food or drink, whatever they want to put it in. We see a lot of people putting it in things like coffee or tea, but also food is okay. They have to text us or email us for compliance just because we can't watch them do it every day. So that's kind of the next best thing. And then we also have them keep track of what they're eating for the 3 days prior to each of their visits, and we have them do an online questionnaire.
Yeah. So we'll get into a little bit of our subject population. These are the characteristics of our subject. Megan just talked about our intervention group, the 2-week fructose challenge, as we call it. We also had a control group, and these were just subjects that came in for 2 different visits, separated by 2 weeks. They would consume the 75 grams of fructose. All basically this table is telling you is that we had a healthy subject population. So BMI was within normal range. 19 to 25 is considered normal. Our control population was a little bit older than our intervention group, but cholesterol levels were normal, triglycerides were normal, blood pressure normal, and then fasting blood glucose was normal. And these are all just measures that we use in our study to determine whether or not we classify someone as a healthy, lean subject. So these are all healthy subjects in our study. Getting into our main results, these are the FGF21 levels. On the left side, you have the intervention group. On the right side, you have controls. We also separated it by males and females, which we'll talk about later. But these are our baseline FGF21 levels. And our results basically found that after the 2-week fructose intervention, there wasn't really any significant change in FGF21 levels for either the intervention or the control group. Same thing with the stimulated levels. The axis is different here. You'll see that this is the 2-hour peak time, but we don't really see a significant change in the 2-hour stimulated FGF21 levels either. However, we did find a significant increase in fold change in the intervention group. This is an approximate doubling. And when I say fold change, it's basically a calculation that we did. We took the 2-hour peak time and divided it by the baseline value just to see how many times someone increased in their response. And we don't use the stimulated value because there's variability within our subject population. So for example, someone can go from 15 to 45, or someone can go from 100 to 300. It's still a fold change of 3. And so we did fold change instead. But we found a doubling there. And then this is a table to show you that the 2-week fructose intervention did no significant, well, they didn't do any damage to our study population, thankfully. That'd be kind of bad if it did. So I'll kind of it's a lot here, so I'll kind of just walk you through some of the metrics that we studied. ALT and AST, they are liver proteins. A high level of them indicates damage to the liver, no significant change. Whew. Same thing with glucose, insulin, and HOMA-IR score. These are all metrics to determine how someone breaks down sugar, glucose specifically, and stores it. No significant change there. Same thing with triglycerides and non-esterified fatty acids, also known as NEFAs. This just shows basically how fructose is metabolized and how, again, the liver is functioning, and no significant change there either. So there was no damage to the liver or any of the metabolic processes after this 2-week intervention.
So we see kind of a paradoxical thing when we look at our main results. So we see a change in the fold change, which is just a calculation based on the peak and the baseline values, but we don't see a change in peak or baseline. So that's kind of weird that we see that. So now we're kind of going to examine why we might see that. And our hypothesis is that it's based on biological sex. So we did see in our previous graph that females were generally had higher levels of FGF21 than males. So we think that maybe they're responding differently to the fructose. So we see here fold change is significantly increased for both males and females. However, if you break it down by the baseline value and the peak value, so right before they drink the fructose and then 2 hours after, we do see some differences by biological sex. So if you look at the graph on the, your left, the 0-hour graph, the black is before the intervention and the gray is after the intervention. So you see females are higher than males. And we see that males stay the same after the fructose intervention, but females decrease their baseline values. That's not quite significant, almost there. We're going to recruit a couple more people before we actually publish this data, but almost there. So we do see a trend there. Hopefully it'll stay. And then with the peak values at 2 hours, again, the graph on the right, we see females are staying the same, but males are increasing their peak values. So they're doing it differently. So there's a different mechanism by which males and females are increasing their fold change, which might be why we see a difference in fold change, but not in baseline or peak values. So switching gear a little bit, we did look at diet as well. So this is a correlation between fold change of FGF21 and fructose intake, average fructose intake. So this is that online questionnaire we talked about where people rated their average diets. We do see a positive correlation, meaning that higher fructose intake is associated with a higher fold change of FGF21 on this oral fructose tolerance test that we do. So this just kind of supports our data saying, okay, fructose does have something to do with this.
And we also used diet to further explore the question of variability between the subjects that we were seeing. So you're looking at the baseline FGF21 graph again. You saw this earlier. I'll talk a little bit more about the male and female differences here. As you can see, like a lot of, and Megan was mentioning this earlier, a lot of the males are on the lower end of the intervention group graph, and a lot of the females are on the higher intervention group graph. However, you could even look at the individual points and see that there's variability there. So we felt that diet might be a good way to account for this variability. So aside from the 90-day food surveys that we gave people to assess, their regular consumption of carbohydrates and fructose in the regular diet, we also looked at proximal carbohydrate intake. So we gave people food logs, and they had to record what they were eating and drinking for the 3 days leading up to their visit, and we tried to see how this would influence their baseline FGF21 levels and their FGF21 response. And we did find a pretty moderate correlation with proximal carbohydrate intake, so those 3 days leading up to their visit. Say I had a lot of cake Monday, Tuesday, and Wednesday, and my visit was on Thursday, my baseline FGF21 would be higher than the average person, potentially. We did, interestingly, not find a correlation between proximal fructose intake and baseline FGF21 levels, but yeah, we did with carbohydrates.
So here are our conclusions. Basically, we just see that 2 weeks of fructose intervention does cause a significant change in how we respond to that oral fructose challenge that we talked about. We believe that it might have a protective role, this increase in FGF21. That would be because we don't see any damage to the liver, so we think that maybe FGF21 is protecting us from those damaging effects of fructose. We do see that males and females respond differently to the 2 weeks of fructose, and that's something interesting to explore in further studies. And we also know that diet might influence some of that baseline variability. So we have some acknowledgments. We want to thank Dr. Jody Duche. She supervises our research over at the Beth Israel. Dr. Dean Tolan supervises our research here. He's our on-campus faculty advisor. KHC and Europe for the funding and the support. All of our subjects for putting up with 2 weeks of fructose. And to you all for listening to us talk for 15 minutes. And any questions?
And if you're interested in participating, you can email fructosetrial@bidmc.harvard.edu.
Yes.
Now for participation.
Okay.
Did you look at variables other than sex while assessing the differences?
So we do have some preliminary data showing that age might have something to do with it as well. We do have some older males that show really, really high values. So this triangle that's way higher than the rest in the control group is an older male. And generally, we do see that trend in some other studies that we've done, but we don't have enough subjects to comment on that yet with any sort of confidence. Any other questions? Yes.
So you suggest this amplification in the FGH or FGF after
Yep.
consumption has a protective effect.
Mm-hmm.
And that spike, that amplification or the fold change is larger for males or larger for females versus males.
Yes.
Does that imply or would it suggest that the protection is greater for one sex or the other? Or the required amount of this compound must be different for one sex versus the other to achieve the same protective effect?
That's a good question. I don't think it indicates any, well, as far as we know, it doesn't indicate any gender differences. But what we focused on was the fold change. So oftentimes males and females would both have a tripling or a doubling in this case of their FGF21 levels. But I don't think we know if that means it doesn't indicate that females are more predisposed to obesity or diabetes or anything like that.
We do think that maybe it has something to do with body fat composition because females do generally have higher body fat compositions than males, but we haven't measured that, so that's something we might want to do in the future. Okay.